Hi guys, today we're going to be looking at something called Cavalieri's principle, which is going to apply to two-dimensional and three-dimensional shapes. So to start, take a look at the do now, the figure in the do now, the givens, and think about the two questions there. Find out what their areas are for the two triangles, and then what do you notice about the two triangles, their similarities. Take a second, pause the video, jot down a couple things, and then play it again. Okay, so after calculating their areas, you should have noticed that they have the same exact area. Now, these triangles look different. One seems to be more slanted than the other. So now that you've got their areas, think about what's similar about the two triangles and why they might have that same area, even though they look different. Okay, so you should have noticed that the two triangles, although they look different, have the same base length. They also have the same height, and therefore, after plugging in those numbers into our formula, they end up having the same exact area. So this is an introduction to what we're going to be talking about today, how things might have the same area or same volume depending on specific dimensions. So now take a look at the next part of the do now. Can you draw another triangle between the parallel lines that will have the same area as triangle ABC and triangle DEF? Take a second and sketch in a triangle, and you can add measurements if you need to. Sketch in another triangle in between the parallel lines and see if you can make it so that it has the same exact area as the previous two. Okay, so you could have drawn a triangle like mine in the green. I have triangle GHI, where GI has a length of 4 inches. That would also work as a triangle that has the same exact area as triangle ABC and triangle DEF. Obviously, yours could look different than mine. It could be slanted in a different direction. The main idea here is that it has the same base length. So the base on that bottom parallel line has to be 4 inches. And the top of the triangle is on the other parallel line, giving it a height of 6 inches. So if you drew any triangle that's got a base of 4 inches and that extends to the top of the other parallel line, then you know you've created a triangle that's got the exact same area as the other two. Okay, and this is going to lead us into our definition of Cavalieri's principle. So take a second and read through what I'm going to print on the blank lines below. Okay, so the two-dimensional version of Cavalier's principle supposes that two regions in a plane are included between two parallel lines in that plane, and it states that if every line parallel to those two lines intersects both regions or both shapes in line segments of congruent lengths, then the two regions have equal areas. And as you can see in the two diagrams underneath the definition, what that means is between lines P and Q, which are parallel, if you were to draw in multiple other parallel lines, when they hit the two shapes, they create equal line segments or congruent line segments. And if that happens, then you know that those two shapes, even though one is a rectangle and one is a parallelogram, they will have the same area. If you take a look back up at the do now, it would be as if we were to draw in parallel lines across our shapes, all three of our shapes, and those three line segments should be, and if I draw another set as well, should all be the same length since the triangles are congruent, and that's also going to show that the triangles are congruent in area. Okay, so if you flip the page, we'll take a look at number 1 and see how we might apply Cavalier's principle to a diagram and see what types of triangles will be using that principle and which ones wouldn't. So for number 1, you're given two diagrams. Identify which pair of triangles applies Cavalieri's principle. So taking a look at triangle 1 and triangle 2 in the green, and then the two purple triangles. Take a second, pause the video, and think about which one demonstrates that definition that we just filled in on the previous page. Okay, so after studying the diagrams, hopefully you see that the diagrams on the left apply Cavalier's principle. And if you can see, the purple, the red, and the green line segments in each of the triangles are congruent once you draw those parallel lines across. And that really comes down to the fact that the bases of each triangle are congruent and they're on that same parallel line. They're both on line Q. If you take a look at the second diagram, they are very similar looking triangles, okay? And if we were to calculate their areas would be the same, but we're really looking for where does that definition of Cavalieri's principle apply. So if we were to draw parallel lines like they did in the diagram, T and V, when they cross over the triangles, do they create equal segments or congruent segments? And just looking at the purple and the green segments, you can see that the two purple segments are not congruent and the two green segments are not congruent. What that comes down to is the fact that the bases of the triangles, the fours, are not on the same parallel line. Okay, if they had been, the two triangles would be exactly the same and those parallel lines would cut across the triangles, creating congruent segments. Okay, so the big difference between the two diagrams, in that one applies Cavalieri's principle and one doesn't, those parallel lines cut across the triangles, creating congruent segments. Their bases are on the same line as well. And once you have that, you're applying Cavalieri's principle. Both sets of triangles in each diagram will have the same area, but we really want to know which one fits the definition of Cavalieri's principle. These were all examples of two-dimensional figures that we're comparing to the Cavalieri's principle. Now let's take a look at through the three-dimensional definition and then look at three-dimensional figures. Okay, so now I'm going to read Cavalieri's principle in 3 dimensions. So suppose two regions in 3 space solids are included between 2 parallel planes. If every plane parallel to those 2 planes intersects both regions in cross-sections with congruent areas, then the 2 regions have equal volume. Okay, so what that means is when we look at 3-dimensional solids, okay, and as you can see in the 3 pictures below the definition, if you start to cut those solids using planes like we did on Friday with cross sections, all right, if you start to cut them and you go parallel to the top and the bottom of the figures, as you can see in the leftmost picture here, if you cut them and you start to create congruent cross sections all the way from the bottom to the top, okay, that will mean that the 2 solids will have the exact same volume. Okay, and that really comes down to like we did in the do now, they're going to end up having the same exact dimensions to fill in to our volume formula. Okay, so that leads us to the criteria for Cavalieri's principle. So for 2 objects to satisfy Cavalieri's principle, they have to have the same exact height as we saw in the example with the triangles in number 1. And then they also have to have that the areas of each cross-section must be equal at every height. Okay, so across the 2 figures, if you were to cut them with a plane, those cross-sections, the areas of those cross-sections must be equal at every single height. All right, so let's take a look at number 2. For number 2, we're given a right circular cylinder and an oblique circular cylinder, basically a slanted circular cylinder. And it's asking true or false. If the radii of both cylinders are equal, the volumes of the cylinders will be equal because they have the same height. So thinking back to Cavalieri's principle, the 2 criteria that are that the heights must be equal, which will be true in our case, and that the areas of each cross-section must be equal at every height. Now think about the figures or the shapes that will be created if we were to find a cross-section, a horizontal cross-section, across each of these cylinders. If I were to cut each of these cylinders horizontally, what kind of shape would we see on the inside? Well, it would have to be a circle because the base of each figure is a circle. Now we know that each cross-section will have the exact same radius. What does that mean then for the area of each of those circles? Will they be the same? Thinking about our area formula, if I plug in the same radius for 2 circles, they will have the same area. We've now satisfied both of the criteria for Cavalieri's principle. The heights must be equal, we're given that, and that the areas of each cross-section must be equal at every height. That circle is never going to change as we keep cutting cross-sections of the cylinders. So now we know that the area of each of those circles will be the same. because it meets those two criteria, we can say that this is true. They will have the same volume. So a written out answer to this question might look like what I've printed here, true, because their heights are equal and the areas of each cross-section are equal at every height. Those are those circles that we would keep cutting cross-sections of. Okay, so let's take a look at the next page, number 3. Morgan tells you that Cavalieri's principle cannot apply to the cylinders shown below because their bases are different. Do you agree or disagree? So taking a look at our two figures, we've got a rectangular prism, possibly a cube, and a cylinder. Think back to the two criteria for Cavalieri's principle, that the heights must be equal and that the areas of each cross-section must be equal at every height. Take a second, think about it. Could Cavalieri's principle apply here, or could it not, and why? Okay, so hopefully after looking over the criteria, we can come to the conclusion that we can actually disagree with Morgan, that Cavalier's principle can apply to these figures, and that's because they can very easily meet just those two criteria. Though if they have the same height, okay, and if the areas of their cross-sections at every height are equal, then we know they'll have the same volume. Okay, so we can have the base of the rectangular prism and the base of the cylinder have the same area. That will lead us to having the same volume. And what it really comes down to is that once the two bases have the same area, I'm really following that volume equals the area of the base times the height. If the heights are exactly the same, okay, and the areas of the bases are exactly the same, then there's no reason why the volumes would not be the same. They might be different shapes at the base, but if they have the exact same area, then there's no reason why the volume can't be the same. And that's what we're getting from Cavalier's principle, that their heights are the same, and if the areas of their cross-sections at every height are also equal, then they're going to have the same exact volume. Okay, so taking a look at another two figures that are different, let's take a look at number 4. So the bases of the following triangular prism T and rectangular prism R lie in the same plane. A plane that is parallel to the bases and also a distance 3 from the bottom base intersects both solids and creates cross-sections T' and R'. All right, so we have a couple of jobs here. We need to find the area of both of the cross-sections, T' and R'. We also have to find the volumes, volume of the triangular prism T and the rectangular prism R, and then we want to answer the question, what can we conclude about these figures and whether Cavalieri's principle applies to them. Okay, so let's pause the video, start by finding the area and the volume of the triangles, the rectangles, and then the prisms. Okay, so first I found the area of the two-dimensional figures, T' and R'. So first I found the area of the triangle. That is really the cross-section of the triangular prism. I used our formula, area equals 1/2 base times height. So the base of the triangle here is that 10 along the one side, and the height is the altitude, that 3.3. So 1/2 times 10 times 3.3. Gets us our area of 16.5 units squared. Then I also did the same thing for the area of R' using our base times height formula, and we're getting those two dimensions from the sides of the rectangular prism. So I have 4 times 4.125, and that also gets us 16.5 units squared. So now that we've got our two areas, you can notice that they are exactly the same. So before finding the volume, think for a second, what does that mean that the volumes might be? What might the volumes have in common? Since the areas of the cross-section are the same and the heights of both prisms are also exactly the same. They have the same height and they have the same area of the cross-section. So think about what that means for the volume and then go find it. Okay, so hopefully you saw that really just to find the volume, all you had to do is multiply each number by 5, multiplying by the height, and then we end up getting the exact same volume. Not really that shocking, because since we had the same height of the prisms and the same area of the cross sections, it then follows that we should have the exact same volume for both figures, even though they have different shaped bases. So for E, what can we conclude about these figures and whether Cavalier's principle applies? We can say that it definitely does apply here, since they have the same height and the same area of the cross sections. Okay, so looking at number 5, we're given a right circular cylinder and a right rectangular prism. We want to answer true or false. Cavalier's principle does not apply to these solids because their bases are not the same shape. So what we've just seen from the previous problems is that it does not matter if the bases are not the same shape. We can have a triangular prism and a rectangular prism, and they can still satisfy Cavalier's principle. The only things that we need are equal height and the equal area of the cross-section bases. Okay, so as long as we have those two criteria, two figures, they might not have the same base shape, but they can still satisfy Cavalieri's principle. Okay, so I'll read number 6, and then you're going to take a second and think about the answer for it. The three solids shown below have the same height and matching cross-sectional areas parallel to the bases. Which of the solids have the same volume? Justify your answer. So you're picking A, B, C, or some combination of those. Which ones have the same volume? Okay, so hopefully after reading that question, you'll see that all three will have the same volume because all three of the prisms satisfy those two criteria for Cavalieri's principle. They all have the same height, and they'll all have matching or equal cross-sectional areas parallel to the bases. So if we were to slice them all across like this, okay, all of those figures we would create parallel to the base, in each one of them would have an equal area. Those two things will satisfy Cavalier's principle, meaning that all three of them will have the exact same volume, even though they are different shapes, they have different shaped bases. For number 7, use Cavalier's principle to explain why the volumes of these 3 stacks of books are equal. It comes down to the same thing. If you notice, if you were to count how many books are in each stack, they have the exact same height, so their heights are equal. And then the areas of each cross-section are going to be equal at every height because you can see it's the same book throughout the 3 stacks. So using our criteria for Cavalier's principle, we know then that the volume of these stacks of books will all be the same. Okay, so for number 8, by Cavalier's principle, this right triangular prism and the right rectangular prism have the same volume. If the center plane intersects the solids parallel to their bases, which of the following choices could be the base and the height of the triangular cross section? So we know that these prisms already fall under Cavalier's principle. So we know that the red rectangle cross section in the rectangular prism and the red triangle in the cross section of the right triangular prism are going to have equal areas. So in order to find out what the dimensions should be for the height and the base of the triangle, we really need to know what the area of that rectangle is. So to find the area of a rectangle, we want to use area equals base times height. We know that the base and the height are 6. So we know that the area of that rectangular cross-section is 48 units squared. Okay. We can also take a look at some of our options, and now we know that the height and the base of the triangle have to create an area that is exactly the same as the rectangle, or 48 units squared. So take a second, take a look at some of the options, and see which one fits the dimensions of that triangle that has to have an area of 48 units squared. Okay, so hopefully you found that choice B, where the height is 8 and the base is 12. Those two dimensions on that triangular cross-section will give us an area of 48 units squared, which we know is exactly the same as the rectangle, since these two prisms fall under Cavalier's principle. So at this point, you finished the packet. You can go ahead and ask the sub for the homework. You can get started on the homework and refer back to these notes or refer back to the video for any help you might need. And I will be around after school today if you have any questions, and I'll see you guys tomorrow if not.